in the early 80s when I was out, a young programmer. Actually, I was kind of old back then too. But so here's our starting point, 1936. Alan Turing is probably the first person to write code that you and I would recognize as code, that executed in an electronic computer, used binary as its instruction format, and you and I could look at it and say, yeah, that's code. So here he is, and he has invented, by 1986, the concept of a computer that you and I would recognize as a computer. A little weird, this funny little tape that goes back and forth, but still something that you and I would consider a computer. And then in this paper, he writes code that you and I would recognize as code. He invents other things as well. He invents subroutines. He invents macros. He invents variables. He uses binary. You see that relay there? Who's used a relay? Anybody here use a relay? Yeah, a bunch of electronics people, good, okay. A relay is just a coil of wire, and if you pass current through that coil, you get a magnetic field, and the magnetic field will attract that little piece of metal right there. It's called the armature. It'll pull it in. And as it pulls it in, it grabs these switch contacts here and pulls the switch contacts in, so you can either open or close a switch contact by using an electric signal into the coil of that relay. These were invented for telegraphs, because a telegraph signal could only go so far, maybe 20 miles or so, and then you had to amplify the signal, and what they would do to amplify it is that they'd put a relay in there, and the relay would energize, and that would close a new switch on a new battery and send the signal another 20 miles. That's why they call it a relay. It relayed the signal. Now, a device like this can probably switch 10 times a second reliably. So the kind of clock rate, if you want to use that term, that Turing was able to get on his machines was something on the order of, 10 milliseconds, 100 milliseconds, something like that. It was a slow clock rate, but much faster than anything anybody could do by hand. So most of the time they depended on relays until late in the war, where they started to try to use vacuum tubes. They built the Colossus out of that. They kind of got some results, but it wasn't very reliable. By 1945, though, they'd begun to solve some of those problems. The war was over. That's good. The ACE was a machine that Alan Turing helped to design. He designed the instruction set. He designed the word width. He designed the concept of the machine. The machine would be able to add, not subtract. In order to subtract, you had to reverse the bits and add 1 to do a 2's complement. What kind of memory do you think this machine used? How many gigabytes do you have in your phone? How many gigabytes are in this room? Right now. Right now, how many gigabytes are in this room? The original concept for the ACE was to use these mercury delay lines. Now think about this, right? A mercury delay line is a tube of mercury, fluid, right? And you put a speaker on one end and a microphone on the other, and you pump audio signals in at very high speed, so you wouldn't actually be able to hear them, high-frequency audio signals into the speaker. The sound waves roar through the mercury, come out the other end where the microphone, a transducer, picks them up, and you cycle it around to the beginning of the tube again. This was rotating memory, very much like a disc, except it was sound waves going through the tube. They figured they could get 1024 bits into a tube. That was their goal. They wanted to get 1024 bits into the tube, and then they would have 22 such tubes, because this machine was a 22-bit word size machine. So this was going to be a 1024 by 22 machine that they would write code on. In the end, they had to give this up. They couldn't get the mercury delay lines to work properly. And so they had to fall back on a less efficient option, which was cathode ray tubes. It turns out that if you spray an electron beam at a screen, like a television set does, the beam will leave some residual charge. Actually, it depletes charge. It creates this well of depleted charge on the screen. And then you can sweep the beam over that well and detect the repulsion from the screen in the outgoing beam. And you can see where bits had been written. Of course, that destroys the bits, so then you have to refresh them. So that's kind of cool, and Turing took great use of this because this was his output device. He would read his output on the memory itself by looking on the screen. A bunch of bits, ones and zeros, just hanging out there. He used a scheme of not hexadecimal, he used base 32. Base 32 is ideal because all 26 letters of the alphabet and the numbers don't quite add up to, you get a little bit more characters than that. So he would just do everything in base 32. 1945, this guy, Alan Turing, is writing real code that we would recognize in binary, base 32, reversed, by the way. He wrote it right to left for whatever reason. 1945, the number of computers in the world on the order of 1. Probably more than 1. There were a couple of others, different people who were making computers at the time, but probably no more than 4. And the number of programmers in the world by 1945, big O of 1. Probably more than 1, maybe 10, 12, something like that. But fairly small number of programmers in 1945. Tubes got mass-produced in the 50s. For all kinds of reasons, computers weren't the only reason. People were starting to listen to radios and stuff like that, and televisions. Now, here you see a little bit of Fortran code. 1953, by the way, was the year that Fortran was invented. John Bacchus submitted the Fortran spec in 1953. This is the year after I was born. We wrote our code on this stuff. That's a coding form. And you would write your code in number 2 pencil in these little squares here with capital letters. And we used a lot of erasers. In this time, programmers did not type. We did not know how to type. We would write with our hands in pencil on these coding forms, and then we would take a stack of coding forms and we would hand them to the key punch operators, who all hated us because we were interfering with their real work, which was data entry. Right? And the key punchers, when they would deign to, would take the coding forms and they would then punch them onto cards, and you'd get a card that looks like this. And then 24 hours later, if you were lucky, you would get your deck back from the key punch operator, and you'd take it back to your desk, and you would look at every card. You could see the code printed on the top of the card. So you'd just kind of thumb through the cards and make sure the cards were all right, okay. And they weren't, because the key punch operators didn't know what they were punching. They were just kind of punching anything that was on the form. And if you weren't careful with your I's and your O's and your 7s, they would print 1s and 0s and T's. And so you had to be real careful with that to be real, make sure they understood what you were printing. You'd take this deck of cards once you eventually got it right, and you'd take it down the hall to the computer room where you'd put it in a basket with a rubber band around it. And put it in a basket, and then you had to back away from the computer room because programmers were not allowed to touch the computer. Programmers were not allowed in the computer room. If you backed away far enough, then the computer operator would open the door slightly and take your deck inside and then shut the door. And then he'd put it in another basket because the computer operator was busy doing real computer stuff. They had jobs to run. They had bills of materials to do and payroll stuff to do and all this other stuff to do. They were busy. So by maybe 3 in the morning, one of the third shift's operators would finally see this deck of cards in the basket and say, crap, all right, I'll run this. And put it in the card reader and push a button and read the cards in and compile your program and do whatever test you wanted and print a little printout at the end. And he'd tear the print off and he'd wrap it around your deck of cards and put a big rubber band around it and haul it out to the table outside and put it outside. And the next day you would come in and there would be this thing on the table and you'd take it to your desk and you'd untake the rubber band off and get the cards set aside and start thumbing through the listing and, oh, forgot a comma. Right? The turnaround time was 24 hours, if you were lucky. Sometimes it was longer than that. And the time just to get your deck punched was 24 hours. This was the life of a computer programmer in those days. Now, to deal with that, we worked on 5, 6, 7 programs at the same time. So we'd always have several in the queue. That's the life of a programmer during those days. 1958, Lisp is invented. McCarthy invents Lisp. By the way, that was the beginning of functional programming. Between 1954 and 1960, IBM sold 140 Model 709 computers. In 1960, the number of computers in the world was on the order of 100. Might have been 200, might have been 500, might have been 700, but it was on that order. And the number of programmers was on the order of 1,000, because in those days, a single computer required 10 or 12 or 15 programmers to keep it running. We had no operating systems. We had no function libraries. We had no frameworks. If any code ran on those machines, we wrote it. So we needed a lot of programmers to keep those machines alive. They weren't trained in school. They weren't CS grads that were drawn from the industries they had been working on. And they were old. They weren't young. They were in their 30s and 40s and maybe their 50s. They were people who were mature. The transistor was born. And the transistor replaced the tube. And the transistor was more reliable than the tube and drew much less power than the tube and could be mass-produced more cheaply than the tube. And so very rapidly, the transistor dominated the market. By 1965, there were 10,000 1401 computers. 1401 computer was a really interesting machine. It was a decimal machine. Now, you can't do it in decimal. You still have to do it in binary, so they used binary-coded decimal. They would rent these machines for $2,500 a month, which sounds like a lot, especially when you think that that really amounts to $20K per day, but it was enough for companies to consider bringing a machine like that into their facilities and dealing with their information management problems. And by this time, I'm 13 years old. From 1945 to 1965, 20 years, there's perhaps 100,000 programmers in the world, but they didn't graduate with a computer degree. There were no computer degrees. There weren't enough engineers, scientists, and mathematicians. There weren't any computer science grads. Accountants, planners, clerks, anybody with a technical bent. Anybody who might think in that funny way that programmers think. And if the company trusted them enough, they would be brought in as programmers. They would be moved from their current job to a programming job. And these people were, again, older. Though not mathematicians, they were experienced, disciplined professionals, and I like to think that Turing would have approved. He might have shirked and said, well, they're not mathematicians, but at least they're disciplined. I actually worked on machines like this one. I worked on an IBM 36030 and an IBM 36040. The 30 had 16K of core, 16K bytes. By this time, we had identified that there was a thing called a byte, right? And it had 16K. That one was kind of out in the lab where you could sort of touch it. And then there was an IBM 36040 that had 64K. That was back in the computer room. You weren't allowed to touch that one. I remember when we got our first megabyte. It was later than this. And a megabyte would have fit, see that blue box over there? This roughly the size of a restaurant freezer. That would have been what a megabyte looked like. And you didn't go near it because it rented for tens of thousands of dollars a month. If you wanted to buy it, it would have been tens of millions of dollars to buy. It was a very valuable piece of equipment. By 1966, same era, Ole Johan Dahl and Christian Nygaard, operating out of Oslo, created the Simula 67 language, which was the very first object-oriented language. By 1968, Edsger Dijkstra had written his famous paper, Go-To Considered Harmful, and had begun the structured revolution, structured programming. Here you've got Ken Thompson and Dennis Ritchie, 1968. We're still only 22 years after the first code had been written. These were the years that I started writing software. These are the years that I got a job. That's me at the tender age of 18. Actually, I think I was 19 there. Already a programmer, by the way. Already hired as a programmer to work at a place near my home writing COBOL. God help me. I remember being in high school, touching computers in high school. We had a teletype that would hook into a computer at the Illinois Institute of Technology. At my first job, there were about 24 programmers, most of them in their 30s or 40s, and half of them were women. That was at that place where I was doing COBOL. Now, what's changed? Well, the hardware's changed. Think of the difference between a PDP-8 and my laptop. PDP-8 had 4K of core. That thing's got 16 gigabytes of RAM, and that's considered small nowadays. PDP-8 had 32K words of disk. That thing has a terabyte of SSD. Not even a disk anymore. Just a terabyte of solid-state memory. And if you add up all the differences, you can very easily convince yourself that that machine there is 22 orders of magnitude more powerful than a PDP-8. Okay, now here's an iPhone. How many transistors are in here? And he speculates. He says, at least a trillion. At least a trillion transistors in here. Now, what if you did that in tubes? You'd need a trillion tubes. Now you can do some very interesting math. How big a building would you need to house a trillion tubes? And the math there works out to be, I believe it was 170 vehicle assembly buildings. The big building at NASA, the biggest building in the world, 170 of those, just to house the tubes. It would mass as much as 2,500 Nimitz-class aircraft carriers, the biggest aircraft carrier made. It would require a lot of power at 1 watt per tube. It would require a terawatt, requiring us to build, 500 2-gigawatt nuclear power plants, the biggest nuclear power plants we built. It would cost, $50 a tube, $50 trillion, the economic output of the world. And once you had built it, there would be no one to call.
Or how about that phone call that Nixon made to the moon that's 250,000 miles away? When I can't get a signal on my cell phone line, I guess phones were better in '69. Well, do you still believe we went to the moon? Do you still believe what they're telling you? Just connect the dots and pretty soon you'll find out what I found out too. But if you question this stuff, you'll be labeled a loon. You'll be called a conspiracy theory buffoon. But I don't care, man. I'm still gonna make this too, cause I know that we didn't go to the moon.
And it certainly has to be the most historic telephone call ever made in the White House.
Yeah, you went straight through those Van Allen belts. It wasn't a problem, right? Nothing was felt. But now you say it's a problem and you can't get through. This problem needs to be solved, according to you. But didn't you solve that problem back in '69 and you flew straight through them 5 more times? You wonder why I think it's fake when there are so many Apollo mistakes, like the telemetry data that's all gone missing. 13,000 reels, are you kidding? A giant leap for all mankind, but you lost the data and no one can find. Come on, man, are you kidding? Do you still believe we went to the moon? Do you still believe what they're telling you? Just connect the dots and pretty soon you'll find out what I found out too. But if you question this stuff, you'll be labeled a loon. You'll be called a conspiracy theory buffoon. But I don't care, man. I'm still gonna make this too, cause I know that you can't go. No, there's no blast crater from the lunar module. Probably because that thing is just a model. Or the flag that flutters with no atmosphere. Don't you think that's a bit queer? Intersecting shadows means another light source. Do I think it's fake? Yeah, of course. The whole thing was filmed on a Hollywood set. Directed by Kubrick is my best bet. The moon's so cool, we'd love to explore it, but we can't get past low Earth orbit. Do your research, people, I think you'll find that NASA admits that a bunch of times. Listen.
Right now, we only can fly in Earth orbit. That's the farthest that we can go. And this new system that we're building is going to allow us to go beyond and hopefully take humans into the solar system to explore. So the moon, Mars, asteroids, there's a lot of destinations that we could go to, and we're building these building block components in order to allow us to do that eventually.
I'd go to the moon in a nanosecond. The problem is we don't have the technology to do that anymore. We used to, but we destroyed that technology, and it's a painful process to build it back again. Build it back again. Back again. It's a painful process to build it back again.